Linear or nonlinear control? The choice.
Systems can be broadly classified as linear or nonlinear. Linear systems are approximations of reality. They are usually simpler to analyze and design, with well-developed tools like transfer functions and frequency response methods. A linear system typically has a single equilibrium point. Its stability does not depend on initial conditions, and it avoids complex behaviors such as limit cycles, bifurcations, or chaos. In linear systems, frequency and amplitude remain independent. Nonlinear systems, on the other hand, are more realistic but much harder to analyze. Their tools are still developing, and they can exhibit multiple equilibrium points. Stability often depends on the initial condition. Nonlinear systems may show self-sustained oscillations called limit cycles, undergo bifurcations where equilibrium points change with parameters, and even display chaotic behavior where tiny inputs cause large, unpredictable outputs. In these systems, frequency and amplitude can be coupled. This contrast highlights why linear systems are favored for simplicity, while nonlinear systems capture the true complexity of the real world. Linear systems are defined by the principle of superposition. This means two things. First, if you multiply the input by a constant, the output is multiplied by the same constant. This is called scaling. Second, if several inputs are applied at the same time, the total response is simply the sum of the individual responses to each input applied separately. This is called additivity. Together, scaling and additivity form the foundation of linear system behavior, making analysis and design both predictable and powerful. When improving existing control systems, one of the first steps is to account for neglected physics, those subtle dynamics that were previously ignored. Beyond that, we must explicitly address nonlinearities. Hard nonlinearities, such as saturation, dead zones, or hysteresis, introduce discontinuities in system behavior. Strong nonlinearities, on the other hand, arise from higher-order terms in a Taylor series expansion, making the system's response far more complex. By tackling these nonlinearities directly, we can also deal with model uncertainties more effectively. This approach not only simplifies the design process, but can also lead to better cost and performance optimization. In short, embracing nonlinearities and uncertainties doesn't complicate control. It can actually make it more elegant and efficient. To analyze and design nonlinear control systems, engineers rely on a variety of powerful techniques. One of the most intuitive is phase plane analysis, which provides a graphical view of system trajectories. Lyapunov theory offers a rigorous mathematical framework to assess stability. Moving further, differential geometry methods, such as feedback linearization, allow us to transform nonlinear dynamics into simpler, linear-like forms. Another practical tool is the describing function method, which approximates nonlinearities for frequency domain analysis. We also draw on optimization theory, including variational optimization and dynamic programming, to design controllers that balance performance and constraints. Finally, modern intelligent techniques, such as neural networks, fuzzy logic, and genetic algorithms, bring adaptability and learning into nonlinear control, making systems more robust in uncertain environments.
We truly appreciate your subscription and support.